an active member of the pavement materials community, serving on editorial boards for leading engineering journals. And Dr. Cetin, the floor is yours.
Thank you, Pat. Sorry for the long introduction there. You feel free to cut it next time. So, do you guys hear me okay?
Yes, Bora, we hear you. Thank you.
Okay.
Yes, sir.
And let me. You see the full screen, right? Not the presenter mode?
Yes.
Yes, sir. You're in presenter's mode.
Okay. All right. Thank you, Pat, for the nice introduction, and thank you, Preview, for leading this effort and all other consortium partners. I'll try to be in my time limit, 15 minutes for the presentation. On the topic is that actually 4 consortium partners are working together on this use of innovative geosynthetics to improve the resiliency of highway embankment slopes under extreme climatic conditions. And the partners are from Michigan State University, Preview, and A&M University, Arizona State University, and Texas A&M University. I'm the PI, Dr. Aldam Pupala and Dr. Zapata were the co-PIs from each consortium partners on this, and our students Fayaz, Avinash, and Camila were the ones who work on these projects. And here is our consortium partners. So overall introduction, this idea started with the improving the slope stability of embankments that are highly used in transportation infrastructure. The main focus is still there, but we also wanted to add some pavement embankment durability, not only slope, but entire durability, stiffness, and shear strength performance improvement of highway embankments. And just like you can understand from the title, Michigan State is in the northern part of the country, and the rest is on the other 3 consortium partners are in the southern part of the country. So the climate is completely different. In Michigan, we have extreme numbers of freezing and thawing cycles, and we have frost susceptible soils, which can be significantly impacted by these freezing and thawing actions. And in the southern part of the state, especially in Texas and certain parts of Arizona, we have a lot of expansive clays, and with the rainfall or flooding events that start increasing, number of these events starts increasing significantly. And if you have expansive clays, that causes that is subjected to wetting and drying cycle, that causes significant infrastructure problems as well. For instance, with expansive clay, the main thing when you have the wetting process happening, it swells, and when the weather gets high and dry very quickly, it shrinks, and that causes significant problems. Similar problems with frost-heavy soils, frost susceptible soils, I would say, when you have the presence of moisture and weather start freezing, volume of the ice is higher than the volume of the water. It expands, put a lot of heat pressures and distress to the roadway systems from the embankment, and it causes some longitudinal cracks, fatigue crackings, and when it thaws, actually, that's when we get the majority of the damages. With the thaw settlement, we call this as freeze-thaw strength loosening. The bearing capacity of the highway embankments are lost, and this loss can be too significant, and soil is very wet. The embankment soil is very wet, so there are some spring load restrictions happening. So here are some of the examples of these failure of roadways happened because of this freezing and thawing or wetting and drying cycles. And you would be shocked to hear the results. The damage caused by this expansive soils and frost susceptible soils that are subjected to wetting and drying cycle and freezing and thawing cycles. The damage caused in terms of budgetary is 10 times higher than damage caused by these hurricanes, flooding events, and even earthquakes. So these are not as sudden, crazy failures like we see in flooding events, earthquakes, or hurricanes and storms, but annually, U.S. needs to deal with these two type of problems. So it's really a major problem. What are the typical conditions for slope failures and in general highway embankment performance? You have problematic soils. Two of them are, as we mentioned, is the expansive soils and frost susceptible soils. And environmental conditions. In one case, you have the heavy rainfall, and the other one, you have the freezing and thawing cycles and water supply. Water supply is one of the major problem that we deal in geotechnical engineering in particular. I always say if we any time in the future mankind to settle or colonize Moon or Mars, you don't need much geotech engineers there, so because there's not enough water to cause enough problematic soil problems. What are the typical traditional solutions to handle these problems is chemical stabilization or replacement of soils, and mechanical stabilization, whether it's more compaction or drainage improvement, or with putting standard regular geosynthetics. However, those things have been studied, and since this is a new study, we wanted to come up with a little bit more alternative solutions, some innovative materials that are recently developed in the geosynthetic industry to improve the drainage of any geotechnical infrastructure, and when you improve the drainage, that would ultimately improve its mechanical properties. And one of this product, we have another product that we are testing, but I wanted to focus on the geotextile that we called as a kind of Viking geotextile that has Viking fabrics between the patterns there, as you can see the blue lines. And what these Viking fabrics kind of do with the differences between the relative humidities from the atmosphere and within the soil, it kind of start moving the suck the moisture within the roadway system or soil system and remove it horizontally to the sides of the embankments or to the slopes, and try to keep the soil as dry as possible. And here is how it kind of, if you want to give a background, it generates capillary suction, collects that moisture from soil and transport that water for exposed portion, and that water evaporates from that exposed portion. And because of that potential differences, it keeps the soil more drier. So again, if we come to the overall objective, I won't have enough time to go all the details, but overall problem statement again, improve the performance of expansive soils and frost susceptible soils by integrating of this innovative geotextile, and evaluate their performance both in the lab with the large scale testing facilities, small scale testing equipment, and also do some modeling and field testing, and recheck to see is this geotextile is really removing the excess moisture, and does it result in an increase in the stability. And here is the work distribution between the universities. We all did the literature review. It's completed by all the universities, and now laboratory tests have been conducted. Frost heave test by Michigan State University, swelling shrinkage volume is by Texas A&M, and large-scale direct shear test has been conducted by Arizona State University. Both pre-review, TAMU and MSU are doing the field test, and modeling is we start doing some modeling work with TAMU, ASU, and MSU. So we are having good progress. Hopefully next year we will have much more results to summarize in the next year's curriculum. And here are the research questions. The main idea is really to get an idea about short-term and long-term performance of these geosynthetics when we use them in slope stability of embankments under extreme rainfall conditions, basically extreme moisture conditions and extreme winter conditions, and do some field implementations, check to see how it works, and monitor its volume and shear strength changes, and model that, and ultimately check to see if we get a good moisture equilibrium. So we collected two different soils, one from Minnesota frost archetypal silt and one from Texas swelling clay, as our main goal is really to improve the performance of soils in these freeze-thaw conditions and expensive wetting and drying conditions for the swelling expansive clays. And in MSU, what we do mainly frost heave test. Again, I'm happy to provide more information on this later on. We prepare our specimens in 6 inches in diameter, 8 inches in height, and we sometimes put Viking geotextile when we wanted to see the performance of the Viking geotextile on this frost heave test setup. And we put thermocouples with every inch of the specimen and monitor it, and we have heat exchangers on the top and bottom to determine the thermal gradient that we apply to simulate the freezing and thawing of the samples. And we have a water supply simulating the groundwater table source, and that provide the water from the neat. And when we start freezing from the top, that's what happens in the field. We kind of see how much water is being sucked in, and if you put the Viking geotextile at any level at here, and we also try to configure which level that we need to put the Viking geotextile, that would be more efficient to use. And you kind of monitor how much the material, when you apply the freezing and thawing cycle, here is our temperature program, how much during this thermal gradient and temperature scheme that we apply, how much soil is heaved and how much it thaws when you warm it up from the top. And we keep the bottom plate always warm to 4 degrees Celsius. And we kind of monitoring this temperature regime, how the specimen is heaved, how much it heaves and how much it thaws. And we measure displacement through lasers that are put on top of each specimen. And here, the red, I won't again go much in detail. Here is our temperature control per depth for each of our 1 inch high, 1 inch part of the specimen. And the blue line shows the Viking geotextile's frost heave performance, and red line is showing the specimen without geotextile. And as you can see, Viking geotextile absolutely helping minimize the frost heave and thaw settlement performances. So this is one of the first results of our test, and we're running much more tests now, and we also monitor the moisture regimes on each layer, so we hope to have more information in the next meetings. And another work that has been done by the Texas A&M and Preview, we're on the process of building large-scale box tests and run to wetting and drying cycles to check to see and install these sensors, how in the large scale these geosynthetic would work. And the Arizona State and Texas A&M are doing regular direct shear testing and large scale direct shear testing at different moisture contents to check to see the benefit of this geotextile on the performance of these slopes. And last summer in Iowa, we built test sections on an unpaved roadway embankment and placed the Viking geotextile and non-Viking geotextile with similar material characteristics and a control cell, and we put moisture and temperature sensors at different levels and at different horizontal longitudinal directions to monitor first how the moisture is Viking geotextile really sucking the moisture out of the system as opposed to non-Viking geotextile and control section. And also we're monitoring the stiffness values as well. Actually, our team will be there next week to start taking the stiffness and strength measurements before the winter hits. And here is some of the pictures how we installed the moisture sensor couple tree, and here is our data collection system on the ditches of the embankment. And here is the initial data since August. The black line kind of shows the moisture changes over time, and the blue line shows the Viking geotextile and section moisture regime, and the red line shows the moisture regime on the non-Viking depth. And as you can see, the Viking geotextile kind of keeping the water volume lower than the non-Viking geotextile section and control section. And we already pre-review start doing some field application on the large embankment field sites, and I think Dr. Alam would have more information on this. They start installing the sensors and monitoring these performance of these test sites that they have installed just Viking geotextile. And we start curating our numerical modeling work frame to kind of simulate the performance in the lab, performance in the modeling programs. Our specific focus at MSU is the frost action, simulating the frost action and how these Viking geotextile would perform. And the future work really start getting into the large-scale laboratory slope simulation and doing more numerical modeling in addition to the lab work that we have been doing. So I hope I didn't exceed too much. This is pretty much the overall summary of our project. Do we take the questions now, Pat, or?
I'm going to suggest we hold the questions until the end. This way we don't run out of time for our presenters. But if anybody has questions, drop them in the Q&A while they're still fresh in your mind. And we'll try and come back to those at the end, time permitting. So thank you, Dr. Cetin. Appreciate that. That was very interesting. Next up is Dr. Amy Epps Martin. Dr. Amy Epps Martin has more than 27 years of experience teaching civil engineering materials courses and conducting research on safe, sustainable asphalt technologies at Texas A&M University and the Texas Transportation Institute, where she's also the AP Florence Wiley Professor too. Her experimental research focuses on the development of safe, sustainable asphalt pavement technologies. Her research has direct impact on the design, construction, and maintenance of long-lasting asphalt pavements, as evident by her evidence by the adoption of so many specs and standards that she's been involved with. And just an interesting factoid that was provided to me, if I understand correctly, she now has 3 sons studying to become Aggie engineers as well. So with that said, Dr. Epps Martin.
Howdy, can y'all hear me?
Yes.
Okay, great. And I don't think I'm in charge. I'll just say next slide. Is that correct? I just want to verify that.
Yes, that's correct.
Okay. All right. Well, good morning, everybody. Thank you for the opportunity to speak today to you about our Insight project focused on optimizing asphalt mixture performance testing for balanced mix design. This is a joint project between Texas A&M Transportation Institute and Rutgers. Next slide, please. So just in terms of the motivation and sort of fitting this project in with everything that's going on in the asphalt pavement technology world, we're aware that 94% of the 2.8 million miles of paved roads have an asphalt surface. A lot of them are in the rural part of the nation. And that ends up being about a $30 billion industry in hot mix asphalt. So it's a big dollar value. And so anything you can do to improve the performance is going to be a big win because of the volume of materials that are placed every year. You can see the statistics there from the National Asphalt Pavement Association. The most recent ones are from 2022, where 442 million tons of hot mix asphalt was produced. And as part of that, 98.1 million tons of reclaimed asphalt pavement were utilized. It's the #1 recycled material in the United States, more than all the water bottles that we might try to recycle. And still, that's a good thing to do, but we need to keep recycling our asphalt pavements. So right now, the current standard or average, I guess, for all of the states is about 20% of our new hot mix asphalt mixtures, of those 440 million tons produced. About 20% of those our wrap across the country. And so we're trying to up that value. We're trying to increase our wrap contents above 25%. And we want to do that for 3 reasons. The 3 E's is what I say. We want to do that because there's significant economic savings. You see there $4.7 billion in virgin materials costs. There's significant environmental benefits, 68 million yards cubed of landfill space saved and 2.7 million metric tons of CO2 equivalents. So there's significant economic and environmental benefits. But when we do this, we have to make sure that we carefully balance each unique combination of materials. And one of the ways that we can do that is to have mixture performance tests in a balanced mix design system, which is kind of the new paradigm that's being introduced across the country to engineer these modern sustainable asphalt mixtures and ensure a sustainable infrastructure. Next slide, please. So this project is kind of going about, it's a combination project between New Jersey at Rutgers at New Jersey and TTI in Texas. And each state is doing pretty significantly different things. But just as a background, New Jersey adopted balanced mix design for high wrap in 2010. So that's, almost 14 years ago. And they characterize mixtures with repeated loading tests. And I'll show you those in a few minutes. Well, I'll show you a repeated loading test. The overlay tester and the asphalt pavement analyzer to look at cracking resistance and rutting resistance. And they have 5 field sections that this project is monitoring and taking cores on and determining how those mixture properties evolve with time. In 2024, they started adopting a monotonic, more practical test that might be able to be utilized during production of these high wrap mixtures. And that's the ideal cracking test and the high temperature indirect tension test. And the idea there is to be able to make sure that what's being produced and put down in the field still has the balance of cracking and rutting resistance. Texas, on the other hand, adopted BMD for high wrap mixtures in 2019, so maybe less experience, about 5 years of experience. And we are involved in a large implementation project where we're running repeated load tests, the Hamburg wheel tracking test, and the overlay test, and the more practical ideal cracking and rutting tests. Right now, we have about 41 sections across the state of Texas that are in 13 different field projects, which means locations in terms of climate and materials. And the maps just show you that this balanced mix design and what tests are being used is just kind of exploding all across the country. Next slide, please. So for the New Jersey or Rutgers part of the experiment, they first decided to bump up and allow projects to use high wrap contents. And they started seeing that there was significant issues in terms of fatigue life or cracking resistance with their repeated load test, the overlay test. You can see the big drop off in the solid colored bars there. And so they said, okay, we can't just allow this material to come into our mixtures without having a mixture performance test. So they decided they needed to introduce a cracking test and make sure that they're getting at least as good a performance as a virgin mix or a 0% wrap mix. Next slide, please. So their current criteria shows both a rutting test, which is the asphalt pavement analyzer, and an overlay test, which is the cracking test. And it depends on whether they're at the surface, which most of the BMD efforts right now are focused on the surface. And it also depends on what binder grade they're using. The 64-22 is an unmodified binder grade, and the 76-22 is a polymer modified binder grade. And so they have both ends of the spectrum, the rutting end and the cracking end. They also have a few other additional design and production requirements. They have higher VMA to try to get more binder into the mixture because not all of the reclaimed asphalt binder is going to be available. Some of it's going to be stuck to the black and make a black rock in your mixture. So in the New Jersey part of the project, the supplier or the contractor can utilize different cracking strategies, including warm mix asphalt additives, recycling agents, changes or substitute binder grades. They can do all kinds of different things to offset the effects of the stiff, aged wrap materials that are being added at higher and higher contents, as long as they meet these cracking and rutting criteria. Next slide, please. So just to step through a little bit, they have 5 field sections that are a number of years old now, and you'll see that in the next few slides, that are across the state of New Jersey. You can see there with the gold stars. And they have relatively high RAP contents, all the way from 25 at the surface to 50%. Some of them have recycling agents, some of them don't, as a way to mitigate that stiff, brittle material. Next slide, please. So on all of these, they are looking at a combined surface distress index. I'm sorry about the right-hand part of the slide. But on all of these, they monitor the surface distresses, the rutting, the cracking, all types of cracking, non-load associated, load associated, and other distresses. And they come up with a weighted single value, normalized value called surface distress index that goes from 5 for a new pavement all the way down to 0. And when it hits 2.4, that's when rehab would be considered. So that just gives you an idea of how they're monitoring the distress. Next slide, please. So just to quickly step through, this is a 14-year-old pavement, and it still has pretty good performance. You can see the original performance was very, very good on the overlay tester. I think the requirements are in the 200 to 300s, and it was at 1600. And even after 14 years, it's still meeting that cracking requirement on the overlay tester and the rutting requirements from the asphalt pavement analyzer. You can see also that that surface distress index is still very high, and you can see from the picture that it's in good condition. Next slide, please. Going to the next youngest of those 5 sections, this is one after 10 years with a higher RAP content at the surface. Again, the original cracking performance was 350 cycles, and it's down now to 202 cycles, but that's still very good after 10 years. The rutting is still very low. The surface distress index is also still very high, 4.34. Also, you see the International Roughness Index. That's an indication of ride quality, is also being monitored. And anything less than 95 is still in very good condition. Next slide, please. There's another project with a relatively high RAP content of 30% at 10 years. You can see here that the overlay tester results have dropped below the thresholds, but still it's a 10-year-old project. The surface distress index is still not indicating anywhere close to 2.4 for any rehab to be done. Next slide, please. The next one has been out there about 6 years, and it is still showing very good cracking performance, very little or minimal rutting depths on the cores themselves. The SDI is still very high. The IRI is still just dropping, near the threshold between good and acceptable, but still very good. Next slide, please. And the last one has also been out there about 6 years. You can see, again, very good cracking resistance, even after 6 years on the cores, minimal rutting, same story, high surface distress index, and good IRI. Next, please. So overall, they're happy with their implementation of their mixture performance testing with a BMD type system for rutting and cracking performance. And they're currently doing an evaluation that's trying to look at what's making these 5 sections perform so well after 6 to 14 years in service. They've already completed those testing of the cores. You saw the results. And they're doing some analysis on the extracted and recovered binder and the volumetrics that show you how much binder you may have in your mixture. Next slide, please. So switching to the Texas effort, we basically have taken some of the results and added to them for the TxDOT BMD effort. In Texas, we're doing the repeated load testing. You see the Hamburg wheel track testing up there at the top, and the ideal RT, which is the simpler test down there on the bottom right. The thresholds are shown there that are in the current BMD spec, and they're based on the PG high temperature grade of the binder, similar to what you saw for New Jersey. Next slide, please. For the cracking, we're also doing the repeated load test overlay tester, which is the same test as being done in New Jersey, and then the ideal RT, which New Jersey is also doing on the right-hand side there. We have proposed that the threshold should be tied, in this case, to the PG low temperature grade of the binder. Next slide, please. The TxDOT BMD effort has 13 field projects scattered across the state. So again, different climates, different materials, different contractors involved. This effort is looking at the data from some of those projects out of nine of those projects, plus some additional projects that are just been done in the lab. Next slide, please. So what are these different cracking mitigation strategies? I mentioned some of them in the New Jersey part of the presentation, but basically what can we change about the recipe for our hot mix asphalt? We can change the materials, and that has to do with the quality of the materials. So we can change the binder source. We can make it a softer binder, either at the high temperature end, the low temperature end, or both. We can add a polymer modified asphalt, or we can just simply keep the same PG performance grade, but change the binder source. We can also include an additive like a recycling agent or a warm mix additive. And something that's more difficult to do is to change the wrap source and the aggregate source. Usually that's tied to the location and the specific contractor and the availability of materials locally. The other thing we can do is change the recipe, right? How much, the proportions of those materials. So a big thing that people do a lot is to increase the effective binder, which means the binder that's not absorbed into the asphalt, but available for binding and coating our aggregate particles together. So a lot of times the aggregate gradation is adjusted. We can also increase any additive doses. And another thing that an agency could do is to decrease the amount of credit given to the wrap binder. So we can decrease the amount of recycled binder that's available, because that's probably a real thing. Probably between 60 and 85% of that wrap binder is available, and the rest of it is not. The last thing we can do is we can reduce how much RAM we're putting in there. Maybe in some cases, if it's very stiff RAM or wrap, we can't go up to 50% wrap. We can only go to 30%, for example. And sometimes if we have very aged wrap, we have to employ a combination of these strategies. Next slide, please. So we looked at a bunch of different strategies: proportion changes, material changes, additives, and we compared all of them back to a control. And the control is usually a typical wrap content, like 20% or below. And we compared their cracking resistance and their rutting resistance. So this just kind of gives you a snapshot of the different sections that we looked at, some of them in the lab, some of them in the field, and which different strategies we're able to look at. Next slide, please. So this is a lot, but just to complete the presentation, I just want to indicate that we are doing an analysis. And what you're seeing with the black dots is going from the triangle up to the square. That's how much of a jump in wrap content. So remember, I told you typically we're below 20%, and we're trying to go above 25%, in some cases all the way up to 50%. And when we do that, though, we don't want to sacrifice our cracking performance. So we want there to be at least as good as a control or a typical wrap content, which would be the yellow bars. So at least as good as as the control, or even better than the control, as long as we're applying a strategy, which are the green bars. So you can see a lot of different strategies have been applied here. And we want that performance to be at least as good as the control, which is yellow, or better than the control, which is green. Now you do see that there's, in some cases, the red bars mean that it's not as good as the control statistically at a 0.05 significance level. But as long as it's meeting that dash line, which is the threshold currently in Texas, then we're still okay. Next slide, please. The last thing we have to be worried about is when we apply these strategies, we don't want to have a rutting problem. So this is also saying make sure that you don't sacrifice rutting. At least you're as good as the control, which is yellow, or better than the control, which is green. So you do see that in some cases, some strategies create a rutting problem. Next slide, I believe, is the last slide. Oh no, almost the last slide. So in terms of looking at all those strategies together, we note that some mixtures might not require a strategy. Reduced recycled binder availability can be effective across a variety of wrap contents, as gradation change is also important to increase effective binder content. Substitute binders are better for moderate increases in wrap content, and rejuvenators are better with higher wrap contents. We've also looked at plastics, and they can be effective at higher doses across different wrap binder contents. Next slide, please. This is the last one. So the next steps are New Jersey is completing that volumetrics and binder characterization and analysis to figure out what's giving them that good extended field performance. Texas, we're working on developing a guide for these high wrap strategies, like in which cases should we try the different strategies. We're also going to explore the relative cost analysis. And I just want to mention that this project ties in with a lot of different efforts nationally through Transportation Research Board, through a consortium for asphalt pavement and research and implementation, through a BMD implementation working group, and through many current and ongoing NCHRP projects. and FHWA efforts. So it's all tied in together, and we're happy that we're able to do this project. Thank you.
Great. Thank you, Dr. Epps Martin. And you win the award for saying New Jersey the most amount of times in any presentation today. So that's awesome. Thank you. Working with Dr. Tom Bennett here at Rutgers, that's really great to see that collaboration. So thank you. We're going to hold questions until the end if there's time. If there are any questions while they're fresh in your mind, please use the chat Q&A feature to drop the questions in the Q&A box. Our final speaker is Dr. Anol Mukhopadhyay, who is the Senior Research Scientist at TTI and an Adjunct Professor at the Szary Department of Civil Engineering, Texas A&M University. Anol has served as chair of the ACI 221 Aggregate Committee and has been serving as a voting member of numerous technical committees in ACI, TRB, ASTM, and many others. And he served over 27 years of research experience in concrete materials and durability, and has extensive experience in developing and implementing test methods related to concrete durability. He served as an executive board member of the International Cement Microscopy Association and is an associate editor of the ASE Journal of Materials. And is currently serving as an associate editor for the ACI Materials Journal. So with that said, I'll turn it over to Anol.
Hey, thank you. Can you hear me?
Yes, we can.
Is my slide moving?
I think you just say slide and Gracie will index it for us.
Oh, slide is not moving, right?
You just say next slide and all.
Oh, next.
Someone else is going to move it for you.
Hey, yeah, I put your slide up, so I can move it for you if you just say next slide.
Okay. So my presentation is on increasing the lifespan and resiliency of bridge superstructure, concrete through durability-based performance evaluation under the primary pillar of infrastructure durability and resilience. I am the PI from TTI, co-PI from Rutgers, John Burley, and the research team is Ninad from Rutgers, Praveen, Abhijit, and Manoj from TTI. And Manoj is a graduate student working, and he is going to present tomorrow. Next slide. Okay, so this is the main goal of this particular project is durability-based performance evaluation during the mixed design stage and improve service life prediction, which leads to the benefits of extending the lifespan and resiliency of bridge deck concrete, optimizing the investment, reducing disruptions, and ensuring safer commutes for the public. Next slide, please. If this particular slide is talk about the multi-phase concrete deterioration, and the blue curve, it shows the different stage. Primarily the steel, we use steel in the bridge deck concrete, and steel corrosion is a big issue. And you see there are different stage: initiation phase of corrosion, propagation, and acceleration. So when the concrete deteriorates over time, of course, live load in the field is a very important phenomena. So there are two things going on. One is the live load as well as the environmental, which is primarily corrosion of the concrete. And you see the concrete corrode, and it ultimately leads to crack development, delamination, and failure. So if we have a better control on the better prediction of the concrete conditions over time, then what we can do is we can take a better decision for the right selection of the right rehabilitation methods and extend the lifespan and save the repair costs. That's the big deal. But the problem is at this time, we really don't have a better prediction models to do the conditions to do the damages over time. Next slide, please. Okay, so the key innovation that we introduce here, the material level model developed in TTI. We actually develop a model called, tool, text.tool. And based on the tool, we do the durability properties prediction as well as performance evaluation of the cast in place bridge deck mixes during the mixed design stage or trial batch stage, and also field QA/QC stage. That is already developed, and we are going to apply that tool in this project. And then structural level, Rutgers is leading that. They did accelerated concrete bridge deck testing in BEAST, and they develop actually the deterioration curve, that particular, and help to generate the deterioration curve due to live loading only through NDT evaluation, and established a relationship between the ADT and the deck deterioration. That relationship we use to predict the deck deterioration due to ADT live load in the item 2. Item 3, they did a significant amount of NDT evaluation in a couple of bridges, and duration of 4 to 5 years. They develop a damage curve over time due to both life and environment. And then number 4 is that we compare the NDT evaluation and the bridge deck deterioration due to live load, and then try to apply an environmental factor and give a complete picture of but however, their prediction is primarily structural. Material is not included. Ours is material. The structural live load deterioration is not included. So the approach, our goal in this project is an amalgamation of the material level properties prediction as well as structural level to give a potential development of more reliable deterioration and prediction model. Next slide, please. So this is the TTI model that we developed. We develop an Excel-based tool that predict the 4 durability aspect. Number 1 is alkali silica reaction in concrete. Number 2 is a shrinkage based cracking potential. Number 3 is the chloride durability, time of river corrosion, and probability of failure. And number 4 is the freeze thaw durability. Next slide, please. This slide, this is already developed. You don't have to go, that this is a given an idea that this particular Excel-based tool, we give input of material composition, mix design information, and resistivity measurement of the concrete mix. And tool actually use those input and some other intermediate level inputs, and their models are inbuilt, and it calculate based on this model and input, it predicts 4 major durability of the concrete. One is that ASR prediction, how much supplementary cementitious material you need to mitigate ASR, and then what is the amount of autogenous and drying shrinkage and cracking potential of the mix, and then time of corrosion initiation or probability of failure of that mix, and the time to critical saturation as a measure of freeze thaw durability. These are done during mix design stage. So if there is any deficiency in the mix, run with the tool and give the input, and if you see any deficiency, you have still a room to fix the problem before placing the concrete in the field. Next slide, please. Okay, so the test, our job is to reproduce the mix that BEAST facilities in Rutgers. We reproduce the mix and did the sample casting. Several tests is undergoing on, like autogenous shrinkage test, chloride test, freeze thaw durability, bulk resistivity, surface resistivity, alkali silica reaction, and petrography. So sample casting and mix design is, mix design finalization, sample casting is done. And then all the lab tests are in a good progress. And of course, we are going to identify some bridge decks that contains SCM called like fly ash. Go to the next slide, please. So the versatility of the tool, that material level tool that we developed here, that application is, it can do the rapid determination of lab-based properties. Without doing the long-term testing, we should be able to predict those properties. But of course, it needs a tremendous amount of validation. That's what we are going to do in this project. But in future, you don't need those long-term testing every time. You just predict the properties and also predict the 4 durability that I mentioned in the previous slide during mix design time. So these are the tool can be applied, and the performance-based approach during mix design. That's what I told. And also at trial batch, or sometimes field, when the mix, they place the mix, the field truck, you can do using that mix also. So the purpose is identify that it is really a good mix that is necessary for a particular location. If not, then there is still a rectification. And so that if you place a good mix in the real world, it is going to perform long time and durable, safer infrastructure, and minimize the repair cost. Next slide, please. This is the BEAST slide, the bridge evaluation and accelerated structural testing. This is primarily designed to simulate under an accelerated conditions and evaluate the bridge deck. And it is a chamber. You see the big chamber. Next slide, please. Okay, so this is the BEAST. They placed actually 50 feet and 28 feet, 5 feet thick a deck inside this environmental chamber, and it simulates the load, which is around 17,000 cycles per day. It's a very accelerated load testing. They apply brine salt and also the freeze thaw cycles. So it is under simulated conditions, and try to understand the behavior of the deck within a small period of time, like within 2 years. Can you go to the next? Okay, now they did actually the NDT evaluation after the 2 million live load passes, and to understand the damage over time. You see the left curve, the concrete modulus, they predicted based on NDT evaluation, non-destructive testing. And you see the modulus is changing from 5,000 to 4,400. And then similarly, the right side one is the delamination. And you see there is a entire deck and the middle section of the deck. And it says that condition index, delamination index, at the beginning is around 95, that become around 60. 60 in the middle section, that means 40% of the deck is delaminated in the middle, but the overall 20% is delaminated. So this is the quantification of the BEAST deck. Go to the next. Okay, now they went to the field. Actually, this is called Virginia Haymarket Bridge, where they did manual NDT, non-destructive test evaluation, half cell potential, USW ultrasonic wave, GPR, electrical resistivity, impact echo, and moisture scan. Go to the next, please. Okay, see here, they actually developed the model and predictive capability based on the NDT evaluation. They did a particular bridge from 2009 to 2015, around 6 years time span, and there are 4 data points. This kind of evaluation is necessary. And you see there are individual curve for half cell potential, delamination, GPR, and there is a combined condition index curve over time. And you see here that this is all on an acceleration phase. So your corrosion potential is pretty high, and the combined index is going on, and they try to fit those 4 points. They try to develop a sigmoidal curve, but of course the beginning values are not available. The one important thing is here, if you go to a bridge and if it is an acceleration phase, your frequency to go to the field, it should be more than 2 years, less than 4 years. So if you go to the field and do a real NDT evaluation and damage curve over time, a meaningful curve can be generated a minimum 2 to 3 years time. And our project is 2 years, so it is time bound, so, and actually really difficult to get a complete picture of deterioration curve within this small 2 years project. Go to the next, please. This is a very interesting slide. That's probably the most important slide here. You see here the blue curve, the BEAST curve. BEAST did a 2-year study in accelerated condition. Now they try to predict under field for a particular bridge like Haymarket Bridge, applying the ADT values, and they try to predict the load-only deterioration curve called BEAST, the blue curve. And then environmental loading effect correction is, so they went to the field, spent almost 4 times 6 years duration NDT evaluation, and they developed the field curve. You see here the BEAST curve is the reference curve, and there is a correction for the environment, that's the left curve. So that's an actual evaluation. They did BEAST, then try to predict the load only deterioration curve, and then did the environmental correction. And then the left bridge is RT18 bridge, where the BEAST curve compared with the field curve. That field curve is actually, that correction was actually incorporated without doing the NDT evaluation of that particular bridge. So that is the beauty. That means in the left side, the 2 curve, like for R18, can be generated without going to the field, can be generated because the advantage of the BEAST facilities. So this kind of card can be incorporated in our evaluation. Go to the next. So what is the product, deliverable product that end user is going to use? It is a combine of the material like TTI doing and structural Rutgers is doing. So the materials, we can use our tool to predict we make sure the good mix is applied in the field. It is a durable, good mix. We can ensure that. But at this time, our capability is only that. We don't have the structural evaluation. So now we can add, like the modeling capability of Rutgers, we can incorporate it in a combined format and give aspect 1 and aspect 2 both. And if the engineer are having these two information together, how they're going to use this information for a new construction as well as existing day. Can you go to the next? So basically you see here for the new construction, we are doing our material level that TTI developed. We can do the rapid estimation of the in-field service life, durability performance in terms of shrinkage-based cracking potential, time to chloride-induced corrosion or probability of failure, and freeze the durability during the mixed design or trial-based stage. And structural is going to perform the prediction of the deterioration curve due to live load and environmental effects. That means you'll be fully equipped to place a durable concrete with proper consideration to ADT and environmental challenges, leading to long service life and less repair cost. Next. So, and for the existing deck, what we can generate is a combined approach of material and structural model, facilitate the prediction of damage curve in a very reliable manner. One thing we can introduce that our TTI material prediction is expected to be useful to validate the curve shifting due to environmental effect left side. That is a good thing that we can introduce, which is currently not there. And determination of the right time to apply sealer coating materials or patching or grouting to extend the life and avoid or delay the huge cost associated with demolition and replacement. Next slide, please.
Anol, you have about a minute or two left.
Okay, yeah, this is my, I think the before last. So now the next is we need to identify the bridge with SCM. All the discussion was based on OPC, 100%. Now there are in Texas and other places, the bridge contain SCM. So we need to select bunch of bridge and do the evaluation. Rutgers is going to do that. And then we just take care of the SCM bridge. Next slide. This is the last slide. So the broader impact is the TTI is doing the material level, Rutgers doing the structural level. If we combine together, I think we can generate a very powerful tool or model or predictive capability to reliably predict the deterioration curve, which helps selection of suitable maintenance strategy, save resources by extending the service life during the design stage, which ultimately helps safer commutes for the public. Thank you.
Thank you, Anol. Really appreciate the presentation. And of course, like Dr. Epps Martin, appreciate all the references to Rutgers and New Jersey. You come in second. I think Amy beat you on the New Jersey references. But thank you to all of our speakers. We have about a minute or two for questions. I saw one question come in on the Q&A for Bora. Which was asking about which placements of geosynthetics do you suggest for proper drainage following a large-scale slope failure during your lit review?
Hey, thank you, Robbie. Thank you, Pat. We didn't get to the large-scale implementation test yet, but so far the literature review and somewhat our field experience, the Viking geotextile, this type of geotextiles, you would like it to be daylighted, you excavate it and put the geotextile properly wherever that is failed. Kind of when you're reconstructing it, you rebuild it, put it in a 1 to 2% slope and make sure it's daylighted. And those Viking fabrics should be longitudinal to the drainage direction so they can take it out of the sides.
Great. Well, thank you very much for everyone's participation today, and another round of applause to our speakers. So we're going to be heading back to the main session, which will have the undergraduate student presentation speakers. You're encouraged to please stay for that. Having our students involved in our research is really critical. So please don't ditch out for lunch. Please stay for our student presenters at the 10:45, 11:45 Eastern time slot. So why don't we all head back to the main session now? Thank you to all of our speakers. Thank you.
Thank you.
Thank you.
Thank you, Pat.